second thing is to prove the approximation lemma. I'm going to prove this lemma in two cases. I'm just going to do one case, and the second case you have to do it for yourself. So case 1, consider those processes for which the expectation of step processes, obviously, for which the expectation of f of t and f of s is continuous. Okay? Function of t comma s in this rectangle. Okay, so it's a continuous function. So in other words, you can treat this as a two-dimensional scalar valued continuous function. Okay, so in other words, those processes for which this is true. Okay. For example, what would be the trivial example of such kind of a process actually? The trivial example would be the Brownian motion. So take expectation of w of t and w of s. So what is it? What is it? It's the minimum of s and t. Okay? So imagine that the minimum of s and t is s, so it's equal to s. So is this a continuous function?
Yeah.
It's a continuous function. Okay. By the way, you can ask even a more question that is w of t is an element in L2AD. So is it adapted? So we have assumed the adaptedness. So is it has that definition that if you, for example, take A to B, expectation of w of t square dt, so is it finite actually for this process? For sure, because this is going to be equal to simply t. You can integrate t from A to B and it's a finite thing actually. Okay? So in L2AD, Brownian motion is there and many functions of the Brownian motions are also there. W of square of the W cubes, all you have going to be inside. Anyway, so I'm talking about those processes from L2AD which have which have this property, and I would like to approximate such functions. Okay? Approximate such functions. Okay? So let f is an abstract element in L2AD such that it has this property. The expectation of f, it's a continuous function. Be as described above. Okay? So as described above. So what do we want? I want a function, a step process that can approximate such kind of a function actually. Okay? I'm emphasizing again to make you sure that you understood it. I'm not talking about an abstract function L2AD, okay? I'm talking about those functions which satisfy this. Okay? In the second case, we're gonna take those processes, okay, from L2AD which are bounded. Okay? Which are bounded. Okay? And then the general result actually. So f is an L2AD. So what should be the step process that approximates it? The step process, the obvious step process that approximates is this actually. So let me define ft(n) of omega as, and if the t is in the interval say ti minus 1 to ti, where the I have a usual partition of a to b in the terms of the ti's. So in other words, I'm assuming the same picture that I have kept on assuming that the T0 is A and I have a mash, the Tn is B. Okay, so if I take an arbitrary interval, an instant from the arbitrary interval, then fn of t is basically what? That in that arbitrary interval, take the left endpoint and evaluate it at the left end pointer. Okay. So this would be the fixed value. This is the fixed number actually. That would be a fixed value, for this entire interval actually. Okay. For this entire system. Okay. And this f is what? The same f. Alright. Question. Is this map adopted? Should be. Because it's defined in the terms of f actually. And f is from L to A, so it must be adopted. Its adoptedness is not a problem. The real thing is to prove the approximation actually. So what I would like to show, I would like to show, or maybe the claim is to show that Fn converges to F in L2 AD sense actually. That is, that if you compute the integral of expectation of Fn of t minus f of t square dt, it must be finite. So that's what I would like to show. Because this is going to show that Fn approximates f in L2 AD sense actually. Okay? So let's see that why this must be true.
जीरो में चाहिए बाउंडेड होना चाहिए.
Sorry?
जीरो होना चाहिए बाउंडेड.
क्या मतलब?
एक्सपेक्टेशन.
Finite. Sorry. Okay. This is that. It should go to 0 as n goes to infinity. Yes. Thank you. Should go to 0. So I would like to consider this integral. So let's think about this square first. So here's an interesting thing. So can I say that this Fn of t minus f of t square can be estimated by the 2 times of Fn of t square plus f of t square, right? It's a pretty elementary inequality. A plus b square can be estimated by 2 times of a square plus b square. Okay? And I can estimate this. So this guy has a value in the terms of f of t actually. Okay? So I can estimate this by what? Either I can estimate it or I can take expectation on both sides of the inequality. Okay? Still gonna get the same. And I would say this would be less than or equal to 4 times of the supremum of the f of t square, okay, f of s square, where s is something between a to b. Are we happy with it? I must have expectation as well, yes. Are we happy with it?
T is
So
less
here's
than
the
S.
thing.
T is less than S.
T is
What is the relation between T?
S can be any instant between A to B. So here's the thing. Like this guy is bigger than obviously these both numbers actually. Okay, because T is any instant between A to B actually. Okay. So I'm getting this 4. So I'm getting this 4 that I have 2 already and I can get 2 from here actually. So you can have it 4. Okay? Now treat this as really a sequence. So think about it. This is like Gn. Okay? And this is like G actually. Okay? So when you see this, you remember something. So I have a sequence which is dominated by a fixed function actually. Okay? Dominated by the fixed function. So what should be the next step? Apply the dominated convergence theorem actually. Okay? Apply the dominated convergence theorem. So by Lebesgue dominated convergence theorem, okay? By the way, I don't need to tell you that Fn point-wise will converge to F actually. You know. So point-wise this will converge to F. That's not a big deal. So you have this convergence, and this difference can be dominated by, you know, such a function. So by Lebesgue dominated convergence theorem, if you integrate it, it would still go to the zero actually. So you can have limit n goes to infinity of say hb of expectation of f of t minus fn of t squared dt goes to zero. Treat each of this kind of argumentation as a method actually. Okay? So all these are not just arguments, but these are methods. I mean, if you want to deal with a theory somewhere, imagine you want to define a new kind of, you know, class of processes, and you are interested in defining a new kind of a stochastic integral for that kind of processes. The argument would be analog. Okay, maybe some modification depending on your choice of processes, but argument would be analog. I mean, if you see, in its essence, it's the same argument that we had heuristically in L2AB case actually. That okay, you have, you know, step functions approximated. Now you have the step processes. You are approximating it, and you have stochastic integral for step processes. The next step would be that okay, prove that the, you know, the sequence of the stochastic integral of step processes converges, and converges. You know, you have a definition of a stochastic integral. So it's really the same repetition of argument, okay, but with a bit more sophistication actually. Okay, so I'm just finishing. Case 2, when f is bounded, you have to see it for yourself actually. You should go through it at least, you know, once in your life for that proof. And in case 3, it talks about the generic actually. Okay, so case 2 and case 3 is that if you take an abstract f from L to AD, the same result would still hold actually. In other words, if you have an abstract f from L to AD, you can find a sequence of the step processes that approximate it in this sense. Okay. Second case is that you assume that f is bounded and f in L to AD, and in third case you assume only f is, for example, in L to AD actually. So read through those arguments actually. It's not difficult, it's just manipulation of the same facts actually. And in the subsequent cases, the previous case has been used actually. Okay, so I think this is what is the case. So let me wrap up the discussion, at least at ending the definition of the stochastic integral. So the step 3. Second step is approximations. The step 3 is to meet with this beast actually. Okay, so f of t, d, w of t, okay, when f is in L2 AD. Alright? So, how can I have it? So what I'm going to say? I have taken an abstract L2 AD. My approximation lemma tells me that I can always find a sequence of step processes. Okay? I can find a sequence of step processes that can approximate my given f in L2 AD sense. Okay? The next claim is that the sequence of the stochastic integral of this step processes converges actually. So in other words, since this sequence converges to f, okay, in L2AD sense. So what we will like to prove is that the stochastic integral of, the step process will converge to the stochastic integral of it. Actually, would converge, and we'll give it the name that limit, and basically that limit would be basically, we will call it this guy actually. Okay, the same as the previous one actually. It's not something that is very strange. So this guy converges. Converges where? Obviously in L2 omega. Okay, so we always have I in L2 omega. So how can I show it? So I can show it, prove it Cauchy. Okay, so in order to prove Cauchy, what I need to do, so take the I of Fn, subtract I of Fm, okay, and square it. Okay, and Fn and Fm, they all are step processes actually. So this must be what? This must be I of Fn minus Fm square. So the difference of, so this is a stochastic integral of difference of two-step processes. But we have proved that identity, the E2 isometry type identity for step processes. So this must be same as A to B expectation of Fn of t minus Fm of t square and dt. Okay? This is what is going to be the case. But I know already that I have this convergence in L2AD sense. So what is the meaning of convergence of Fn goes to Fn in L2AD sense? This is precisely what the meaning of it is. So this means that this goes to 0 as n goes to, not n but n and both goes to infinity. Okay? So this means that this sequence of step processes converges, and not only it converges, but okay. So this guy converges, okay, in L2 omega sense to maybe some process in L2 omega, and that process I'm giving it a name actually, A to B, okay, A to B f of t and dw of t. Okay? Obviously you can ask a question, is it well defined? So you can prove it easily that yes, it is well defined, in the sense that if you take any other step function that approximates f, you're still going to get the precisely same limit. Okay? The precisely same limit. You can ask a question, I know when you are doing, for example, Riemann integration actually, I have an easy way to calculate integrals, so that a classical way. Okay? The question is, can we have an easy way to calculate integrals here? The answer is yes, certainly. Okay? So, when you want to make a computation, you don't need any of this theory actually. You can get this theory. Okay? This theory is useful. Okay? In especially difficult situation, but in simple situation. For example, solving a finance problem or maybe a physics problem, depending on Brownian motion, you have direct ways to compute it, like x to the n को integrate करें, so x power n plus 1 over n plus 1. So you will have a similar formula for which you can compute stochastic integrals like that actually. ठीक है? Are we happy with it? Okay. So shall I do one example of it? Okay, based on this theory. Just one example. Or if you are tired, maybe you can do it in next class. Next class. ज़्यादा याद रखो जल्दी हो जाए। अभी कर लें। पॉइंट कितने बजे जाती है?
सर 9 बजे जाती है।
15-20 मिनट।
मानी खत्म हो
हाँ सर, हाँ ये बात है सर,
नहीं होगी खत्म।
ये खत्म हो जाएगी।
बाहर बड़े हो जाए, ठीक है।
होटल में खा जाओ।
सर तो बात नहीं
कल एक बात करना।
चलें। So here's the thing. Let's solve this integral. So imagine I have Brownian square of the Brownian motion a to b, okay, and I want to integrate it with respect to the Brownian motion. The question is, how can I integrate it? Okay, so imagine I'm telling you already the integral. That what would be the integral of it? Can you guess the integral of it? Okay, so if this would be a Riemann integral, so you're going to have something cubed by 3. So interestingly, you have something similar. So you're going to have w cube of, say, b by, okay, minus w cube of a, and everything divided by 3. Okay, so it behaves nicely like previous. But it has an additional term. It would be the Riemann integral of p of t.
By parts.
Okay, it's not really by parts.
Yes.
Not b of t, but w of t.
W of t.
That's p w of t.
Look
Okay.
like by part.
You know, you can't apply by. We don't have by parts here. We have by parts when f is a deterministic function actually. Not only deterministic function, but it has bounded variations. Then stochastic integral will become Riemann still is. We can't have by parts. But okay, this is what my claim
Look
is.
like
Okay. So I want to show that the integral of this is this. The question is, how can I do it? So here's the thing. So here my process is f of t is like w square of t actually. Okay. So I would like to check, does this f have that, case 1 property or case 2 or case 3 property? So let's check it. So f of t, f of s. So I'm doing this by definition. So obviously it's going to be complicated. Okay. So I'm telling in advance actually. So you want to compute limit by definition. So you remember real analysis course actually? It's pretty nasty. Not that nasty, but But if you stick with the definition, if you stick with your recipe that you followed in the proof, you can easily compute it. So f of t, s of t is going to be the expectation of w square of t and w square of x actually. Okay? So one exercise for you where s is obviously less than or equal to t, one exercise for you to show that this is equal to st plus 2s square actually. How are you going to show it? How are you going to compute it? So the real trick would be that in this w square t, add and subtract ws actually, minus ws and plus ws, and then split the square and make your computation of the square. So in other words, write this as w of t minus w of s plus w of s square actually. Okay. And then, treat this as a single quantity and single quantity, simplify, and you will see that you're going to get this. Okay, so that's a hint for you. Now, is this a continuous function in SNT? It's a polynomial function, so it's a continuous function in SNT. So, I need to find a step process that can approximate my, this function actually. So what was the step process that we discussed in, say, case 1 actually? So what was that step process? That you take your function, okay, split your domain into, a to b and everything, okay, and evaluate it at left end point in each actually, okay, left end point for t in the interval minus 1 to t. Okay? Evaluate it at the left hand point. So, do I need to prove that Fn is going to converge to w square of t, I don't need to do because we already have proved the lemma. So this step process would work. Okay, this would work. You don't have to verify everything that the way you did in in your lemma, because you already have lemma, so you can use it. Use it. So if you want to find the stochastic integral of this, compute the stochastic integral of this and take the limit and see what you get. So whatever that limit is going to be the stochastic integral of this. And I'm going to show that limit is basically this guy that you want. Okay? So I need to do what now? So I need to compute A to B, Fn of t and dw of t. So what will be this as a sum? So it's going to be sum, okay, I equal to 1 to n w square of ti minus 1 times the increment of the Brownian motion. Okay? So w of ti minus w of ti minus 1. Okay? So what would be my final goal? I would like to compute this limit actually in L2 omega sense. That's what is my goal. Okay, so just finishing. Keep an eye on clock. Don't miss your bus. Okay. I can stop it at any instant whenever you're gonna say me. Okay. How can I have? So the trick is this. I'm using this elementary identity. Okay, so shall I tell you or shall I just directly write it? So the a minus b cube is a cube. बचपन में पढ़ा करते थे. Minus 3a square b. I think आप बता देना भाई. 3ab square minus b cube, something like that. Okay. So I have a term like this actually, or maybe like this. Okay. So if I want to write this, so what I need to do, so I'm taking this on the other side and this on this side. So I have a term 3a square b in the terms of the rest of the quantity. So I'm just directly writing it and we will get into that what I'm trying to do. So I have 3 times of the sum I equal to 1 to n. Okay, b w of ti minus 1 square, w of ti minus w of ti minus 1, okay, this would be same as, okay, w of b cube minus w of a cube minus sum I equal to 1 to n w of ti minus w of ti minus 1 and everything cube, okay, and minus 3 times of I equal to 1 to n w of ti minus 1 times w of ti minus w of ti minus 1 square. Okay, so I have this expression. So what I would like to do, so okay, I'm not going in all detail, okay, so this is something for you to do. So I'm doing what? Take the square of the both sides, okay, and compute expectation. My claim is, and obviously you're going to have an expectation actually here as well. So think about it, it will not be that difficult to compute this expectation, okay? Because this guy is constant, so not going to make any difference. So we have some kind of a minus b minus c square type thing actually, okay? So my claim is that you can estimate this, you don't have to believe on me, verify it, okay? So I can estimate this by the 15 times of, making all simplification, 15 times of ti minus 1 cube actually. Okay, so this is estimate that we have to verify, and this is same as and I can estimate this by 15 times of ti minus 1 square times the maximum of the ti minus 1, okay, where the I runs from say 1 to n. Okay, so what are you going to say? This guy goes to 0 as n goes to infinity, because this maximum will go to 0 as n goes to infinity.